Hello, everyone. Welcome back to Semi-Analysis Weekly. On this week, we've got Cam, Kimbo, and Brian, and we are going to talk about everything InferenceX. The latest InferenceX article included a whole review about DeepSeek V4 and what it takes to go from like day 0 performance to day 43 performance, meaning how much do these guys grind over the month. So I'm really excited to dig into some topics here. We're going to talk about the model itself, the implementation, how it's running on different hardware, some of the nice vLLM versus SGLang Twitter drama that's been going on, an agentic benchmark that we're working on, and yeah, lots of fun stuff. So guys, welcome to the show. Excited for this one.
Super excited to get started. Let's go.
Nice to
Thank you,
be here.
Jordan.
Awesome. All right, Kimbo, let's start with you. I think the burning question maybe for the general audience here is like, what's different going from DeepSeek V3 to V4? And when you describe what's different, like what impact does that have on running InferenceX? In other words, like what does day 0 support actually mean when it comes to a new model architecture?
I think the headline changes or the features of V4 compared to V3 and R1 would be the 1 million context length. This ability, in order to achieve or to get to 1 million context length, DeepSeek did like very aggressive innovations on the attention mechanism. That's like the first thing. And the second thing is the Mega MoE to like speed up things, to speed up the expert FFM computations. First, the attention mechanism. DeepSeek V4 comes with 2 variants of sparse attention. One is the compressed sparse attention and the heavily compressed attention. So both of them are built on top of the previous version, DeepSeek Sparse Attention, that came out with 3.2. The idea is that by sparsifying your attention between query and the key values, you could reduce the memory reads. So that allows you to do 1 million context length without exploding your memory requirements. Both of them, heavily compressed attention and compressed sparse attention, in addition to that, have like one additional embedding compressor, so that further decreases the cache, the size of the KV cache entry. And then after that, there is they both incorporate some sort of sliding window, which then further decreases the KV cache usage. Combined with all this, I think DeepSeek is quoting like around 100, around that order, 100x reduction of the KV cache usage compared to a standard MoE model. And yeah, that's like the headline feature of DeepSeek V4.
Yeah. And it's also a different architecture in terms of like more total parameters, less active parameters when compared to V3. So literally a different model, not just an update to the weights. Brian, maybe kicking to you, what does this mean when it comes to actually getting support from the various inference runtimes, and like what work is required to actually get performance results out of a system on day 0 when the model's released?
Yeah, great question. So there were a lot of changes, not just like, as you say, not just the weights, but the sizes of certain things as well. For example, some hidden sizes and dimensions. So it's not just adding support for like new attention mechanisms, attention blocks. It might also be like changing or tuning certain things that the community thought was constant. Like in this case, it was for NVIDIA, I guess, it was the MHC dimension. DeepSeek, for the previous times, have always released MHC with, what was it? I think half of what Pro used. So V4 flashed and the previous iterations of DeepSeek V3 all use the same hidden dimension. Sorry, not hidden dimension, MHC dimension. But Pro used a new one, which caused a hiccup for NVIDIA on day 0. Yeah, but for the rest of the guys, I guess, everyone adopted quite well. On day 0...
Like it's worth mentioning, right, that some companies like vLLM and SGLang had like early access under NDA, but companies like NVIDIA like did not. So that made it more difficult to implement on day 0.
Yeah, so I guess they had a head start with implementation. That's why there wasn't as many hiccups. But I don't know if you guys remember seeing it, but there was a Twitter on Twitter, there's this video circulating of like Huawei talking about the optimizations, although it was in Chinese, but someone gave a translation, and there were very good like optimizations talk about during day zero. So like if you just follow what Huawei did, I think you'll get a quite good performance if you're optimizing from day zero. Yeah, but they talked about kernel fusions, they talk about index optimizations. Yeah, it's really good guide, I guess, for day zero optimization.
Wait, one question I had, maybe Kimbo can answer this. I've been reading a lot how about basically this architecture is like extremely kind of tailored to GPU like architecture rather than things like, things based on systolic arrays like TPU. Is there a reason for that? Have you heard that as well, or just kind of curious?
I think solely in terms of what you said, systolic array, I don't think so, because systolic array is essentially like a hardware architecture specialized for matrix multiplication, right? And GPUs literally have tensor cores, which is also specialized for matmos. Models do matmos, so I don't see any very special thing that V4 is specializing for. But I guess I guess what you might see would probably be related to Mega MoE. That is very GPU tailored to GPUs because of the way that the kernel launches and everything. Is that what you're seeing? I'm
Yeah,
actually
I probably, yeah.
Speaking of Mega MoE, what is Mega MoE actually, Kimbo?
yeah.
My
So
basic idea is just that it's a huge fused kernel, but just curious what it is.
yeah, so fused kernel, I think fused kernel is one thing. The whole concept of mega kernel is that you're breaking the kernel, the typical kernel boundaries. So compared to kernel fusion, which is either manually written by kernel engineers, where they just go through the math and they see what can be merged together. Compared that and also like compiler optimization where they remove the kernel launches. MegaKernel is more about breaking the kernel's boundaries that are not typical. For example, sorry, I suddenly can't remember which ones, but some concrete examples of what can be broken is that the register usage. So you can imagine that in a typical kernel, what happens is that you launch a kernel, you do computation. In a von Neumann architecture, you would load data into the register. You do computations in the register, and then at some point you store it back to HBM. So what MegaKernel does is that they fuse different kernels so that they could remove the round trip between data movement between registers and the HBM, while also when a register is free, they could automatically do the next operations of the future kernels. So instead of waiting for a whole kernel to complete. And for Mega MoE, the case for Mega MoE is that in addition to that, they also merged the computation and communication overlap thing. So it's like all merged into one kernel, and then they could do like very aggressive overlapping.
Wait, so what's the downside then of like fusing kernels? It seems like we just fuse everything, right?
Yeah, in the extreme case where we see like the hazy research, they literally fuse a whole model like a llama B, a llama 8B. And I would say that the downside, or I guess the reason that is preventing people from doing that is that it's a lot of engineering work. And in principle, in addition to it's a lot of engineering work, you have to justify it with something, right? So the thing is that Mega MoE is about aggressively reducing the latency. And in a large batch scenario or in a training scenario, it kind of doesn't make sense, or there is a limit to where it stops making sense. So let's say if you're doing a training with a super large batch, like a couple 100 million tokens per batch, your computation and communication is sufficiently overlapped. Your kernel launch time is not the bottleneck. In that case, it doesn't make sense to do Mega MoEs. And the other downside would be, I guess, another difficulty for mega kernels is that it's because of doing like the aggressive resource allocation and on the fly, it creates a lot of memory pressure. So I imagine that'll require a lot of work on managing like the GPUs, I guess, so that they don't, I guess some physics related, maybe they'll overheat or some related issues, which would in turn affect the performance.
Makes sense. Makes sense.
Okay, I want to jump into throw something on screen here. Just a little screenshot from the V4 paper where it explains the open source MegaKernel, and it specifically says two things. One is that it's been validated on NVIDIA GPUs, nothing else, and Huawei Ascend NPUs. Obviously, we've seen the open source CUDA-based MegaKernel called Mega MoE, which then these inference serving runtimes such as vLLM and SGLang and TensorRT can implement for themselves. And the performance improvement claim is somewhere between 1.5 and 1.73 times faster. So clearly they've realized the benefits of this engineering work by doing this. But I want to maybe share a second thing on screen, which is that like the open source community, just because the code is out there, doesn't necessarily have the opportunity to benefit just from day one. And so what we've been tracking really, and Brian, maybe you can take us through this like experience in detail, is how quickly these configs can come online. In other words, how quickly can a given inference serving runtime actually support things. And I thought this little GIF video from the article was quite nice in terms of how it shows the progress over time as we count up the days. And we start to see more hardware being supported as the B200, B300, GB200, GB300 come online, the MI355 from NVIDIA, and then you can start to see the performance improve, right? For people watching, like these lines going from the left to the right means either more throughput or lower latency per user, or, higher throughput per user in terms of interactivity. And yeah, maybe you can take me through like, okay, day zero, there's 2 or 3 different hardware platforms supported. And then a month later, everything's supported. But in that whole time, a lot of performance improvements happen. What are like some examples of some performance improvements that were just kind of like dropped overnight and then were a big win where people can suddenly have, I don't know, 20% more throughput, which means 20% more users or 20% more profitability for the existing users or whatever, for a given inference endpoint provider.
Wait, before I move on to that, huge shout out to our front-end engineer, Alec, for making that video feature. It is very cool and like shows you very nicely how improvements were made. Yeah, and so moving on to the question, I guess one thing that we can like look at these improvements is AMD. Like as the paper said earlier, a lot of the stuff are optimized already for NVIDIA GPUs. And like because of how big the CUDA community is and how many people use CUDA, there was huge incentives for SGLang and vLLM in the limited time they had with the model to prioritize NVIDIA. So AMD catching up is actually a interesting look at like real optimization from getting to work on day zero when. So maybe a first step would be like getting the quantized versions to work. AMD on day zero had FP8 only. There were no native FP4 support, which was quite unfortunate. And actually a very large gains came from getting it to work in FP4. Of course, due to the calculation being faster and lesser memory needs to be transferred. Actually, we have a very nice plot on InferenceX. If you may bring it up, Jordan. Thanks. On the AMD improvements. Yeah, but the biggest jump was converting a lot of the kernels into ITER instead of using torch fallbacks. Yeah, so you can see the SGLang graph actually evolving the most. There's a breakdown of optimizations as well, I think, below in the image. There's a pretty messy image with like orange text in Excalibur. Sorry. Yeah. So there were very big improvements just from changing kernels from torch fallback into ITER. or Triton or etc. So it's very cool to see like the impacts these individual improvements have. And of course, not just like a humongous step, it's always step by step. You optimize one part and you optimize another. Yeah, but very cool stuff.
I want to like take a second to just talk about how cool this is and also shout out all the AMD engineers and NVIDIA engineers that we work with, because this is all of them. Like, we contribute a few things to upstream, like kernel libraries and stuff, but I mean, we're just a team of 3 people, and this is all of the engineers. But I think this is something that's so cool about InferenceX, and like this was the whole thesis of it, the project. Like when we started it, is like, a lot of things online, a lot of benchmarks, you just see like the end product in terms of performance, but really it's like a lot of hard work, tiny iterations, increasing throughput by 5% at a time, and that eventually compounds to sort of, get performant. And like you can see that here, right? So whenever new models release, like Minimax M3 just released, we're doing the same thing. And over the course of a month or two, you're going to see like, you start out with PyTorch, just Torch native fallback, and then you kind of use custom kernels, and then you make the custom kernels even better, and then you just keep making them better and better and pushing the frontier forward. So yeah, this is really cool to see.
I also find it fascinating when I look at these things and you dig in to try to understand what these optimizations are. Like every single one of them, if you tease out just that one optimization, like if you look at the tune parallelism point, or if you look at the fuse KV compressed tile lang point, it might seem simple in isolation, and in some cases maybe obvious that people should have been doing it. But if you try to reason about the entire system all at once, where there's all of these improvements always constantly happening, it becomes like incredibly complicated. And that's really what's so impressive about watching these engineering teams work, is like the ability to take all of these individual optimizations and then build them all together into one thing, which is just like better performance or more efficiency. Super cool. Okay, the next thing that this obviously leads to is the bit of the comparison between the different runtimes. You guys are big on avoiding the war between vLLM and SGLang, the Twitter drama. Can you talk about maybe the reason for this, and why, in some ways, having the competition between different open source inference engines as well as vendor specific libraries is actually driving a lot of innovation and improving things, instead of just like waiting for somebody to be nice enough to share what they've learned? They're kind of, many of them are forced to innovate really fast in order to stay ahead.
Yeah, I mean, we tend to stray away from comparing vLLM to SGLang on InferenceX specifically, just mainly because we didn't find it beneficial necessarily to have like make it a competition. We more so just wanted to showcase each one in isolation. But on the other hand, it does kind of create some competitive spirit, which makes both sides move faster, which can also be a problem because we only have limited compute to run things. So when you double the amount of submissions on a certain model, it's kind of like a lot of CI time. But yeah, we've seen great improvements by both vLLM and SGLang, and I think a little bit of competition is good. But
And what about the vendor specific libraries? We can talk about like some of the other chips, but maybe the most open or easy for us to run is NVIDIA and AMD, because we have NVIDIA and AMD GPUs. Talk about Huawei in a second. Both of them have closed source proprietary libraries in the form of like TensorRT with Dynamo for NVIDIA, and then Atom, Aider, MoE, all the libraries from AMD that make it up. But they're not, I guess, they're not the vendor specific libraries that are closed source are not always the best performance and don't always allow you the most customization. So like, what's the maybe open source versus closed source dynamic that's going on when you guys have to try these things out?
the way I think about it is TRT-LLM and, like Atom, the Aider optimized engine for ROCm, is they're like hyper specific to certain AMD and NVIDIA architectures that will run really fast, but they're not necessarily like completely portable. and not always 100% open source. Like, whereas vLLM or SGLang, you can fork it and go start like your own base 10 together, whatever fireworks. It's very like user friendly, and has API specifications and such. So that's kind of how I look at it. But I don't know, maybe Brian and Kimbo have different opinions.
I mean, in my opinion, it's just more competition. I mean, on our benchmark, we also have a disclaimer saying that Atom has no customers. Yeah, but that's the other problem. If your market just isn't, or rather isn't as big as NVIDIA's, like unless your product is really, really much better. Like MoE is a lot better though than the previous fork. Yeah, but Atom, the development is okay. Development is fast. AMD is putting support into it, which you'd like to see. But yeah, SGLang is just, there's much more help from the open source community, kernel development, which is really good. And Atom just needs that gap, I guess. And who knows, maybe it'll take some time for that gap to close. And Atom gets more accepted by the community, I guess.
I mean, they have like 20x less engineers, so it's kind of... Kimbo, I have a question for you. Like, one of the things that I've been asked before and I've seen on Twitter is basically like, why SGLang and vLLM? Like, why wouldn't SGLang just copy all the good parts of vLLM and vice versa? Whereas, it's to the point where they basically just converge to the same thing. I mean, we're talking about inference, right? We're talking about being 1% faster or something, right? And like everything is kind of being worked out in the open. So it doesn't have to be you, Kimbo, but like maybe Jordan and Brian, like, why do you think it's a natural thing that there are basically precisely two, maybe like a few other like open runtimes, and they're so like head to head, and we're not necessarily converging on like one inference engine? I mean, it is kind of an interesting topic. Like,
Based on my understanding is that, so first of all, objectively speaking, both of them came from literally the same Berkeley lab. They are lab mates. So that's the thing. So they started with a similar idea in the same lab. They started a project, and apparently something happened between them. Some, like the major maintainers, the major project developers, they have some palms between them, which I honestly don't know what happened. And then they just parting ways and having very similar ideas. I think in principle, they are doing the same things, and throughout the development, throughout these years, they are, like you said, copying features from each other. I'm sure you probably heard from our collaborators a lot that on the other side is copy pasting our code and to support this feature. I've heard both sides, so there's that. And
the easiest analogy is like, why does OpenAI and Anthropic exist? Like, they were all one company, and then Dario was working on safety stuff, and something happened, and then he left, and now they really drive each other in a way that I think is benefiting the ecosystem, because they both land counterpunches, and then we benefit as they improve quality and drive prices lower.
yeah, I think TLDR edition is good. It's interesting that they're very similar. They have
I just want to say one other thing, though, which is that I don't think it's completely a historical artifact the way Kimbo describes it. I think there's obviously stuff that's downstream of these runtimes now, whether it be customers or other libraries that depend on them. And so having two different providers allows you to make a decision about who's going to prioritize your features, who's going to merge your stuff, where you're going to get support from, how you're going to work with vendors, because they're just like one point, and there's stuff that's upstream of them, like the vendor-specific libraries in some cases, or like the hardware, literally CI testing, InferenceX stuff. And then there's stuff downstream, which is like, RL libraries, like you look at Slime, or you look at Verl, or you look at PrimeRL and stuff. Like, if there's features that they want to see from the runtime, they need to make a choice and go with the ones that are going to support them. And there's many customers, like you mentioned, the inference endpoint serving providers, as well as the labs. We know companies like Microsoft are using these technologies. They don't have their own stuff in-house. Poolside talked about that in their paper, GLM, the whole thing's SGLang, right? So a lot of people depend on this stuff right now. And I think that's like, it's at least good to have two options to buy from in open source if you're somebody that's making a library and you need support from somebody, and you can have runtime backend support if you really need to, if you're really not getting what you want from the community and you need to go somewhere else. The other, okay, not to take this in too far a direction, but I really want to hear about Huawei, and this is making me think a lot about proprietary runtimes and software experience and like what this NPU chip is going to look like when there's a lot more users, and it goes from what we thought was one or two lines in a paper saying, yeah, we have Huawei support, and then no real proof. But Brian, man, there's real proof now that DeepSeek is running on Huawei. Can you take us through what you've found and the analysis that you did on the numbers that they shared?
Yeah. So actually, before that, I'm gonna talk about like the DeepSeek delays, there were a lot of rumors on X. Because DeepSeek was like planned to release on Chinese New Year, and then it got pushed back and back and back. And every time it was like, oh, it's gonna drop this weekend. Oh, never mind, it's this weekend. Yeah, so there were conflicting reasons. Some people on X were like talking about that's actually trying to get the model working on Huawei. That's why they were delaying it and like optimizing it first before releasing it. And of course, there's the other explanation of like they just wanted better evaluation results. But regardless, the performance on Huawei during release was real. There were benchmarks and like profiles shared by the Huawei team. And looking at profiles, they were very, very elegant. The kernels optimization, as I previously mentioned, were quite sophisticated at that point. So they probably did get much longer access than vLLM or SGLang to optimize for the architecture. And yeah, in the future, we would release another follow-up article on this regarding Huawei's results and comparing it with other chips. Yeah. I think the biggest...
I don't want to distract you too much, but I'm curious if you can compare the state of the software toolkit from Huawei to where things sit with some of the other chips like NVIDIA and AMD. I know you haven't used it hands-on, but in theory, the software is open source and it can now run a close to frontier open source model, like one of the best open source models in the world. So this chip or this system has like come a long way, right?
Yeah, but like you mentioned, their code is all open sourced, same as the vLLM or SGLang. And well, if you want to look at it, you have to go to a Chinese version of GitHub. It's called Git code. But the documentation is very good.
The code is open source, similar to vLLM and SGLang, but not similar to TRT from NVIDIA or Atom from AMD.
Yeah,
in other words, you can read how they implement the kernels.
Yeah, and it's all on Git code, and it is very interesting to see how they do things, like compared differently to NVIDIA or AMD. Their documentation, in my opinion, has been very good. They do frequent meetups in China, where you can talk to they call it CAN, CANN, and you can talk to the CAN developers during meetups. And they have like weekly calls, I think. They have a schedule of weekly calls where you can hop on and talk to engineers. So, like, our take from this is just that Huawei is very enthusiastic about getting this working and open source contributions on CAN. So yeah, the direction has been very good. Some minor notes is that like Huawei has implemented some optimizations from like papers, I think slightly before NVIDIA. Like the one I talked in the article was about fusing communications and computation kernels. If I'm not wrong, NCCL released it in 2024, something like that, but Huawei released it much earlier, right after the paper on it was released actually, which is quite interesting to me. I mean, the Chinese developers are indeed 10x developers, and their velocity is actually great and will be compounded with open source. Yeah, thanks, Jordan. The MC squared. Yeah, and their velocity will definitely be propelled by the Chinese open source.
Yeah, fascinating stuff. Kimball, let's bring you in here. When you hear this stuff about support on Huawei, and then you see something like DeepSeek V4 Pro 75% off discount at the start, which then becomes permanent, what does that make you think for the future of like open source model competitiveness with closed source models if they're just going to try and drive the price down to zero and run it on Huawei hardware? Or whatever GPUs they can get their hands on.
Yeah. So first of all, it's pronounced Huawei. There's an H in there. I'm a bit too annoyed by this.
Sorry.
No, it's my bad. I have an issue. So yeah, okay. Aside from that, yeah, I think ever since we see ZAI with GLM are able to serve their models on Huawei Ascend chips. We also see like this time DeepSeek V4 can do that too. It shows that Huawei chips are getting there, being like a very strong option in addition to what we know from the GPUs and the TPUs. And Chinese have a very different ecosystem. They built a lot of things on their own, like Brian mentioned, the HICO, the MC squared and everything. And the engineers have been very aggressive in optimizing everything. I think the accumulation of all these things end up with DeepSeek being able to offer a very low price. And I imagine that one of the reasons that they could probably keep the price is that they've also pushed a lot more optimizations since release. While I would also suspect that they are trying to capture the market. Based on my understanding is that the chat or the AI model market for China, ByteDance is still like taking the majority. So everyone else is fighting for market share. So they are trying very hard at the cost of probably negative margin or at least just zero margin, trying to get people to use it. So that's why they could serve at a very low margin. And so I think that's like the two main things, two main implications.
Makes sense, man. Cam, you think David versus Goliath? You think that's the right analogy for Huawei to everybody else?
Yeah, dude. I think so. We'll see. Maybe Huawei is actually Goliath. We don't
Right.
know yet.
It's a David versus
Thank you, Cam.
Goliath, man.
David, yeah.
Cool. All right, guys. This has been quite the tour of everything DeepSeek V4 on InferenceX. Cam, maybe we could leave by talking a little bit about future. You got some big work coming with the agentic benchmark. Everything we've done so far has been fixed input and output sequence length. So like, what's coming new?
Yeah, so one of the things with Minimax M3 and DeepSeek V4 is the 1 million context length. Right now, obviously on InferenceX, we are not testing that. We're testing fixed sequence length, 8K, 1K, 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 which nobody uses. But I said this in the last podcast, and it's still good to have the 8K, 1K, and the 1K, 1K because it's showcasing, just in my opinion, basically pure chip performance, right? There's no prefix caching or anything like that. So we're moving it up and we're going to showcase, I mean, inference is a systems problem. So we're moving up the stack. We're going to showcase, we're going to run an agentic benchmark with real Claude code traces that we've collected internally. We're going to showcase things like Dynamo and KV block manager, other sort of KVBMs, and showcase like different PD disag optimizations. And I think it's going to be really cool. And that's going to come in the next couple of weeks. So be on the lookout for that. Yeah, that's all I have to say about it right now, but it'll be really cool when it comes out.
Excited for it, man. Cool. Okay, guys. Anything you think is left unsaid on this stuff so far? Anything about DeepSeek or future plans or InferenceX in general that you guys are looking forward to?
You think, Brian? Do we have anything else upcoming that we can talk about? I'd say B.
Agent X?
Yeah, Agent X. That's what we were just talking about. So that's coming in the next couple of weeks. But I'd say be on the lookout.
chips.
Yeah, be on the lookout for new chips. We have quite a few in the pipeline, so that should be really, really interesting. Yeah.
Awesome. And Kimbo, maybe next time we can talk about RL system performance as well. I know you've been doing a lot of work there. Some of it depends on the inference runtime, but there's much more to an RL system performing well than just having a fast runtime, right? So cool, guys. Well, this is a great show. Appreciate you taking us through this. And if anybody wants to find you, InferenceX on GitHub, find us on Twitter, making memes. Maybe it creeps to LinkedIn and YouTube sometimes as well. More
YouTube
memes about wide expert parallelism and related topics. Yeah. All right. Thanks for coming on.
Thanks,
Nice
guys. Bye.
Thank you, Jordan. Thank you, everyone.